About 13.81 billion years ago, something amazing happened. Our universe began. It is widely believed that it all started out in a very hot, dense state. It became our universe when the matter began rapidly expanding. This is what we call the Big Bang. This theory was first proposed in 1927, less than 100 years ago. Our understanding of the Big Bang theory brings us all the way back to 10 to the negative 43rd second after the universe began. The Big Bang released tons of energy in the form of photons at very high temperatures. Just 4 seconds afterwards, the photons began forming protons, neutrons, and electrons. After 3 minutes, the protons started forming deuterium, which is just 1 proton and 1 neutron, and helium nuclei. As the universe cooled and expanded, nuclear reactions ceased. The universe continued cooling and expanding, and around 400,000 years after the Big Bang, it eventually turned into the galaxies that we see today. Since the Big Bang, we know that our universe has continued to expand, and that expansion rate is accelerating. This observation of the expanding universe is known as Hubble's Law. And no, Hubble's Law doesn't have to do with the Hubble Space Telescope, although they were named after the same scientist, Edwin Hubble. He observed the expansion of the universe by looking at the speed at which galaxies are moving in space. You can liken our universe to a loaf of raisin bread. When the bread is baking, from the perspective of any raisin, all the other raisins in the bread are moving away from it. But that doesn't mean that that raisin is in the center of the loaf. This analogy is used to explain why Hubble's Law doesn't do anything to prove that the Earth is at the center of the universe. In fact, Earth isn't even at the center of our solar system. This is what our solar system looks like today, but it didn't always look like this. 4.5 billion years ago, it started out as a solar nebula, which is a large spherical cloud made up of gases and dust. The solar nebula contracted due to its own gravity and began spinning, eventually forming the planets in our solar system. This leading theory is known as condensation theory and is supported by the way other solar nebulae act in our universe. Our solar system follows a heliocentric model, meaning that the Sun is at the center of our solar system. The Sun is by far the closest star to Earth, and its surface can reach up to 6,000 Kelvin. It radiates a ton of energy, mostly due to a nuclear reaction called the proton-proton chain. The inside of the Sun is mostly full of hydrogen protons, and because of the extremely high temperature, these protons are moving very fast, causing them to fuse together to form a deuteron, which is a proton and a neutron together. This deuteron then reacts with another hydrogen proton to form a helium-3 nucleus with the emission of a gamma ray. When two of these helium-3 nuclei fuse, they form a helium-4 nucleus and emit 2 protons. Energy is emitted during each step of this process because of the conversion of mass. The proton-proton chain happens very quickly and often, which is where the Sun's energy comes from. The 4 planets in our solar system that are closest to the Sun, Mercury, Venus, Earth, and Mars, are categorized as terrestrial planets. The reason these 4 planets are grouped together is because their physical and chemical characteristics are very similar to one another. All 4 of these planets are relatively small, they all contain rocky materials, they all have metal cores, mostly comprised of iron and nickel. Their orbits are very close together, and they are also relatively close to the Sun. Although these planets are similar, Earth is the only one that is capable of sustaining life. The Jovian planets in our solar system are Jupiter, Saturn, Uranus, and Neptune. Their orbits are further away from the Sun, and all 4 of them are gaseous planets, meaning they have rocky cores, but their mantles are mostly made of hydrogen and helium gases. Even though the Jovian planets are much larger than the terrestrial planets, they are much less dense, since they're mostly made up of gases as opposed to the terrestrial planets' rocky makeup. They also have rings around them, but none as prominent as the rings of Saturn. Out of all the terrestrial planets, there are only 3 moons. Our planet Earth has 1 moon, and Mars has 2 moons named Phobos and Deimos. Phobos is the larger of the 2 moons, but both are still smaller than the moon that orbits our home planet. The Jovian planets also have many more moons than the terrestrial planets. Combined, they have 170 moons, compared to the terrestrial planets' 3. The most well-known moons of the Jovian planets are Jupiter's Europa, Ganymede, and Callisto, Saturn's Titan, and Neptune's Triton. As you've probably observed, our moon goes through phases, and not the moody teenager kind. Because the moon orbits the planet and only half of it is ever illuminated by the Sun, we can only see partially illuminated portions of the moon. From our perspective, the moon seems to grow and diminish throughout the month, but in reality, we're just seeing more and more of it as it orbits around the Earth. For centuries, astronomers have studied locations of the moon, planets, and different constellations in the sky. The best way to visualize the sky as seen from Earth is by using the celestial sphere. In the celestial sphere, Earth is at the center, and the Sun orbits around the Earth. We know that this isn't exactly true, but it makes it easier to visualize it that way. Astronomers use the celestial longitude and latitude lines to mark locations of planets and stars in the night sky. As you can see, the ecliptic, which is the path the Sun takes around the Earth in the celestial sphere, does. On Earth, we use longitudinal lines, much like those used to mark locations in the celestial sphere, to separate time zones. Each time zone is 15 degrees wide. Since the Earth rotates at 15 degrees per hour, each time zone represents 1 hour. They start at the Greenwich Prime Meridian, otherwise known as the Prime Meridian. The first time zone stretches 7.5 degrees on either side of the Prime Meridian. As you move westward across a time zone, you will go back 1 hour, and going eastward will cause you to jump forward 1 hour. Since there are 24 hours in a day, and also 24 time zones in the world, the edges of the time zones meet on the opposite side of the world from the Greenwich Prime Meridian at the International Dateline. I know what you're thinking, and no, it is not an international singles cruise. The International Dateline is on the 180-degree meridian, where the time zones meet on the other side of the world from where they started. When you travel across it going westward, your time will remain the same, but the date will change to the next day, and when you travel across it going eastward, the date will change to the previous day. There are 24 hours in a day, 365 days in a year, and that all started billions of years ago with the creation of our universe. Everything we know and everything we are started with that one incredible event, the Big Bang.